Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. The plan for today is we're going to continue our discussion of the congruence axioms. Although it appears I've written on the board the Congruence Axioms. I can't write a C. I've got my usual office hours over the next few days. Today and Wednesday, right after class, and from 2 to 3. Tomorrow at 11 and at 1. As a reminder, we still have a homework set, homework 4, which will be due on Wednesday. Yeah, I know, I'm sorry. I still haven't finished reading your homework 3s. Hoping to get those back to you on Wednesday. I had a grade this exam for my top class over the weekend, so you all are my next priority. In my hearts and in my grading. I don't know what that means. Any questions or comments before we get started for today? A cannibal is going out one day to buy some brains for dinner. Goes to the butcher shop where he's told that a mathematician brain costs $1 a pound, engineer brain costs $2 a pound, and politician brain costs $10 a pound. Campbell's very surprised by this. Asks the butcher, why does politician brain cost so much more than mathematician brain? Is the quality that much better? Butcher replies, oh no, of course not. It just takes a lot more politicians to make up that 1 pound of brain. Okay, so last time we had begun our discussion of the congruence axioms, where we introduced 2 new undefined terms, which is the idea of what it means for 2 line segments to be congruent to each other, as well as what it means for 2 angles to be congruent to each other. Given these undefined terms, we're able to give definitions for what it means for things like one line segment to be longer or shorter than another one, or one angle to be larger or smaller than another one, relying on these 2 undefined terms. We also had a way of defining what it means for 2 triangles to be congruent to each other. Meaning if there existed a 1-to-1 correspondence between all the vertices so that all 3 of the corresponding sides in each triangle are congruent, and all 3 of the angles in each triangle end up being congruent. And finally, we started talking about our congruence axioms, of which there are 6. Keeping in mind that in congruence geometry, we're also still going to be assuming our 3 incidence axioms and our 4 betweenness axioms. And out of the congruence axioms we said so far, we decided that if A and B are distinct points, and A prime is any other point with a ray R sticking out of it, then there should exist a unique point on this ray so that A prime, the segment from A prime to this other point, B prime, is congruent to the original segment AB. In other words, this was the axiom that said we can use the segment AB as sort of a measuring stick, and we can chop off this ray R at the point so that we'll get something that's congruent to the segment we started with. Congruence Axiom 2 says given any line segment AB, we have transitivity of segment congruence, that if AB is congruent to 2 separate segments, then those other 2 segments have to also be congruent to each other. And also, line segment congruence is reflexive, meaning any segment is congruent to itself. Something that feels like a pretty obvious thing, but something that we would like for whatever our definitions here to have to satisfy. And finally, congruence axiom 3, where we said that if we take 2 line segments, AB and A prime B prime, and add to that 2 more segments, BC and B prime C prime, if AB is congruent to A prime B prime, and BC is congruent to B prime C prime, then AC has to be congruent to A prime C prime. So if we start with 2 segments of the same length and we tack on 2 new segments of the same length, the overall bigger segments we would get are going to, or keep saying have the same length, are congruent. Our bigger minor segments that we would get from tacking on equally sized pieces to equally sized pieces are also going to be congruent to each other. And if you recall, I was hinting that one of these 6 congruence axioms is going to be a spicy one, but that we haven't gotten to it yet. Any questions before we move on to congruence axioms 4 through 6? In that case, move on to congruence axiom 4. So if you notice, the first 3 congruence axioms all only deal with line segments. There is no reference to angles in these first 3 congruence axioms. Congruence axioms 4 through 6 are all going to relate to angle congruence, as well in a couple cases to line segment congruence as well. So let's look at congruence axiom 4, which is going to say that given any angle, ABC, BAC, and any ray, A prime, B prime, there exists a unique ray A prime, C prime on a given side of the line passing between A prime and B prime, such that angle B prime, A prime, C prime is congruent to angle BAC. That's a bit of a mouthful. So what this is saying is if we have an angle that we're sort of going to use as our measuring stick, let's say angle BAC, that we started with. And suppose we have some other ray emanating out from a point A prime, B prime. So here we'll have a point A prime and B prime and some point over here. So what this is saying is pick a side of the line going between A prime and B prime. Well, I'll let you choose. Top side or bottom side? All right, we've chosen a side. Your fate has been sealed. Now, basically saying once we pick a side of this ray, either top or bottom, given this orientation, there should exist a unique ray that's going to stick out of A prime. And this unique ray we'll label with a point C prime, so that the angle formed here is congruent to the original angle. Emma, give me another side of this ray other than the top side.
The bottom side.
Good choice. On the other hand, if we had chosen a different side, we would have gotten another unique ray. So let's call this C1 prime. And we'll call this C2 prime. And basically this is saying, given any ray like this, pick a side of your ray, you can always form a new angle on that on that side of your ray, so that the new angle you get is congruent to your original angle. And typically, since rays have 2 sides to them, as we discussed, actually as we proved back at proposition 3.2, back in the betweenness axiom packet, you'll always be able to form exactly 2 rays, one on each side of your line, according to this axiom. Question. Which one of our first 3 axioms is congruence axiom 4 most similar to, would you say? Because to me, it feels like this is sort of saying making a similar sort of statement to one of the first 3. Megan?
It's more similar to number 1.
Why is that?
Because you have a given, I guess length is kind of a weird term, but like a given size of an angle here, where you've given the length of a line segment like a measuring stick, and you're constructing one that's equal.
Yeah, basically it's saying In Congruence Axiom 1, it's saying if you have a measuring stick segment, you can cut a ray off at a point to get another segment that's equal to the measuring stick, so to speak. Here, I don't know, take your measuring stick, snap it over your knee so it becomes a measuring angle. And basically, you can do a very similar sort of thing. Given this measuring stick angle, you can take a ray and use it to produce new angles off of that ray that are congruent to the one that you started with. It's basically saying the same sort of thing for angles that Congruence Axiom 1 said for line segments. Any questions or comments about that? Did this one feel particularly spicy to you, Megan? Yeah, me neither. This is not the spicy one. All right, Congruence Axiom 5. Take Congruence Axiom 2, replace segments with angles. Given any angle, let's call it angle A. If angle A is congruent to angle B, and angle A is also congruent to angle C, then angle B is congruent to angle C, and angle A is congruent to itself. I'm not even going to ask you which of the first three axioms does this feel the most similar to. It's basically exactly the same as Congruence Axiom 2, just for angles instead of segment congruence. I do have a question for you here, though. Why am I not writing out my angles with, like, each of my angles in this case with 3 points, like I did with the angles up here? Here, I just wrote out each of the angles using only a single point. Nate?
Is it because having 3 points would kind of make it too specific? Like it would have to follow along like the other 2 lines. Like if angle BAC is congruent to ABC, then you're making a statement about like the length of the lines too.
That's true. I could say something about if I use the same points multiple times, then I could get a less generalizable result. Okay?
Is it in the first one when you have the 3 letters, is because you're describing the point of 2 separate rays, whereas with doing 1 letter, you're just describing the distance in between the 2 rays instead?
Sort of. Y'all are being too nice to me. There's a 1-word answer that I could give you here. It's shorter. The answer I was going for is laziness. I could say something like if angle ABC is congruent to angle DEF, and ABC is also congruent to GHI, then DEF angle is congruent to angle GHI. And angle ABC is congruent to angle ABC, but A, okay, I don't feel like writing all that out. B, in general, if it doesn't matter for the purpose of what you're talking about, like it's okay to refer to an angle by the vertex at which the angle is taken if the other points don't really matter, and you can see it's clearly understood which angle you're talking about. Obviously, if I have something like this going on, I wouldn't want to talk about. Now look at angle A in this drawing, because you could be like, which angle A? Are we talking BAC? Are we talking about CAD? Are we really getting bad and talking about angle BAD? Are you dab on it? No. In this case, I wouldn't want to just say angle A because it's unclear. There's lots of angles with angle A at a vertex. But if I have something like here, I don't know, ABC, an angle DEF, and this is all that we were given, it would make sense to talk about, is angle A congruent or not to angle D? Because when I talk about angle A in this case, it's obvious what I'm referring to. That one. So here is just a little bit of shorthand, which you can always write it out in full gory detail by referring to every angle using 3 points, and that's technically the correct way to do it. You can sort of just use only the vertex if it's understood what you're talking about. If you don't have like lots of angles going around with coming out of the same vertex, so to speak. Questions or comments about that? Megan, did this feel spicy?
Not particularly.
So what does that mean by process elimination?
Means that Congruence Axiom 6 is the spicy one.
Indeed. So let's take a look at Congruence Axiom 6, which is one you may recognize, but not in the form of an axiom. This Congruence Axiom 6 is our dear friend side angle side. I know, you all probably saw SAS and were probably thinking I was talking about the British Special Air Service, but you would have been wrong. Good, because if you hear of them, you might be seconds away from death because they're coming for you.
But we all just heard of that.
Uh-oh. So, if you have two triangles, where if two sides and the included angle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. Then the two triangles are congruent. So I'm guessing a lot of you have seen this before as sort of like a proposition or a theorem of some sort, maybe in like a high school geometry course. But just so everybody's on the same page, let's say we have a scenario like this going on. Let's say this is it. We have two triangles, ABC, and another triangle, we'll say DEF. What would we normally have to do in order to show that these two triangles are congruent according to the definition of triangle congruence? Yeah?
Show that there is a one-to-one correspondence between each of the sides and then a one-to-one correspondence between each of the angles in each triangle?
Yeah. I would rephrase that slightly and just say a one-to-one correspondence between the vertices that would cause all the corresponding sides and angles to end up being congruent to each other. But we basically need to form a one-to-one correspondence. Let's make this one a little bigger. It actually looks like these are congruent. So here we would need to say something like, oh, let's map A to F, B to E, C to D. And then we would need that AB is congruent to EF, BC is congruent to ED, AC is congruent to FD, and angle A is congruent to angle D, angle B is congruent to angle E, angle C is congruent to angle F. Here I'm using terms like angle A because it's clear that it has to be this one. But we would need all three sides are congruent in this one to all three sides here, and all three angles here are congruent to all three angles here. Congruence Axiom 6 says you don't necessarily need all of that information in order to know that the two triangles are congruent. Instead, if you happen to know that, let's say, that's a lovely line segment, we have a pair of congruent sides, say AB and EF, another pair of congruent sides, let's say AC and DF, and if the angle in between those two sides in each case are congruent, then that's enough to tell you the triangles have to be congruent. Then BC and ED will automatically be congruent, angle E will automatically be congruent to angle B, and angle D will automatically be congruent to angle C. So if I just want to write that out in words, we could say if AB is congruent to EF, and let's say FE. AC is congruent to FD, and angle A is congruent to angle F, then triangle ABC is congruent to triangle FED. If you have 3 of the 6 pieces of information you would need to say that these 2 triangles are congruent, these 3 types specifically, two side congruences, and the angle between those 2 sides match up, then that's enough to tell you everything else will automatically have to hold so that the triangles end up being congruent to each other. Any questions or comments about what side angle side says? I said this one is the spicy one of the 6. Why is this one spicy? Other than the fact that, just like the parallel postulate, it's the last one. That?
It feels like you should be able to have it as a postulate, or not a postulate, a proposition, and then prove it. Because it doesn't seem like you need to have this as an axiom.
Yeah, it feels less axiomatic than the first 5. Sort of like how the parallel postulate felt less postulate-y than Euclid's first 4 postulates. Yeah, I would say that. Congruence Axiom 6 is something that you likely saw in like a high school geometry course as something that you proved, not something that you assumed without proof. In fact, if you look at Euclid's elements, proposition 1.4, the 4th proposition in Euclid's elements, side angle side. So what makes it spicy, I would say, is, I agree with you, Jack, it's similar to the parallel postulate, not in that it's controversial in its truthness, so to speak. It's not like, can't we just draw a counterexample to disprove this? If you try all you want, you're not going to be able to, in R2, say. What's controversial about it is the fact that it feels like a proposition more so than a postulate. Like the first 5 are all saying things, are all much more similar in theme, I would say, to side angle side. And the fact that Euclid himself included this as a proposition, not as a postulate. And don't worry, we are going to look at Euclid's proof of side angle side and talk about why it is a big pile of baloney. That's a little bit harsh. But I'm going to stick with my words. So here's a question. Why side angle side? Why not side side side? Or angle angle side? Or side side angle? Or angle side side? Ass. Well, first of all, because some of those don't work. For instance, side side angle is a pass of lies. So, if you've ever seen why side-side angle doesn't work, here's an example. I can give you two triangles where 2 of the sides are congruent and the 3rd angle is congruent, but the triangles themselves are not congruent. Here's the triangles. Are these two triangles congruent?
No, sir.
Why not?
The angle in between those two sides isn't the same.
Like this angle and this angle aren't the same?
Yeah.
Gadzooks. You can have two triangles where you have two pairs of matching sides. If I really wanted to make it clear, I could just extend this one out by this, by just taking this side and rotating it around a little bit. You can have two pairs of matching sides and a matching angle, but the two triangles are still do not end up being congruent to each other. What's the difference, by the way, between side-side angle and side-angle-side, other than the fact that one works and the other one doesn't? The same three letters, S and A. So both of these are trying to make claims about you have two sides you know are congruent and an angle that you know is congruent. What's different about the way these two look? Zach?
It's the positioning of the angle. The angle has to be between the two sides.
Yeah, exactly. It comes down to sort of this word here, included. Included being between the sides we've already talked about. For side, angle, side, we have two pairs of matching sides, and the angles that we claim that are congruent need to be the angles that are between the matching sides. So here, angle A and angle F, these are the angles that were in between AB and EF, which is one pair of matching sides, and AC and DF, which was the other matching pair of sides. Whereas here, and let's give these names, just so we can talk about it really quick and be rid of it. We have two pairs of matching sides, the sides coming out of angles out of vertex B and vertex E respectively, but the matching pairs of angles are not the angles coming out of B and D, this is the angles coming out of A and D. Angles which are attached to one of the matching side pairs rather than both matching side pairs. In the way SAS is written out, the A is between the two S's to kind of subtly indicate that, whereas with side-side angle, A is not between the two S's. The side-side angle doesn't work. Yes, Luke?
Oh, I was just curious, then why does angle side angle?
Why does that work?
Does that not work?
Turns out angle side angle does work. So out of all the other combinations of that I can make with, let's see, if we go through every other combination of three-letter sequences we can make using S and A. Here's one that works. Angle side angle. As we've already seen, side angle side works, and side angle fails. What other three-letter combinations can I make with S's and A's? Okay. Side angle angle. I'm going to refer to that as angle angle side, which is the same thing just flipped around. Does that one work? It feels like it should not work. And yet it does. What else can we do, right? Side, side, side. Does that one work? And I think we need one more. Right? Ah! Angle, angle, angle. Does angle, angle, angle work?
I don't think so.
Angle, angle, angle does not work because I can have two triangles whose angles are all congruent, yet the triangles are not congruent. Here's my first triangle. There's my second triangle. All right, let's make it look better. Angles are all congruent. You have right angle, and let's say the other angles are 45 degrees. But the two triangles are not congruent, although they are similar triangles. Meaning, if you kind of zoomed in on this one enough, you would get something that looks just like that one. But they're still not going to be the same because the sides are very much not congruent to each other. Proportional, yes, but not congruent. triangles all have to have the same angle sum. That's something we're going to see in a few weeks from now. Which the answer is, nah, yeah, it depends on what else you're willing to assume. In Euclidean geometry, sure, angle side would work because triangle angle sums have to add up to 180 degrees. So if you know two of the angles are congruent, then the third in each case is going to be 180 degrees minus the sum of the other two, and they will have to be congruent as well. So you would get that all three angles are congruent, and you would have a side that's congruent, and then, I don't know, apply angle side angle to say that angle side works. Yeah, would be a way to do that. Would be a way to prove angle side, would be a way to prove angle side using angle side. Here's a spicy bit of information for you. Hilbert, remember this is David Hilbert, came up with these axioms. Chose to use side angle side as his congruence axiom number 6, but he could have chosen any one of these four, because it turns out they're all logically equivalent, assuming all of your instance axioms, all of your betweenness axioms, and congruence axioms 1 through 5. What does it mean to say that that two or more statements are mathematically, let me start. What does it mean to say that two or more mathematical statements are logically equivalent? Something we talked about, I think, kind of early on in the course. Right? Yeah, if they're true in one model, if they're true in one model of the other axioms, they have, if one is true, the others have to be true in that model. If any one of these is false, the others all have to be false as well. So, turns out, if you need one of these in order to be able to prove the others, but if you assume one of these 4 axioms, then the other 3 you can prove as propositions using the other instance, betweenness, and congruence axioms. We're getting a lot of axioms. And yes, there is another packet with more axioms to include before all is said and done. Only one more of this, continuity axioms. So, moral of the story is, side angle side is a little bit of an eyebrow raiser as to its inclusion, and before the end of this packet we're going to have a lot more to say about it. But for now, it turns out to be logically equivalent to the other 3, angle side angle, angle side, side side side, meaning you can use side angle side to prove any of the other 3, but we could have just as easily assumed, say, side 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 as an axiom and treated side angle side then as a proposition which we could prove instead of vice versa. So Dr. Gerstle, why do you think Hilbert chose side angle side? That was as an axiom rather than any of these other 3. If I were a betting man, I would bet because that's kind of what Euclid did. It's not exactly what Euclid did, but what Euclid did in the elements was he first proved side angle side out of these 4, and then used side angle side to prove the other 3. So by treating side angle side as Hilbert's choice of axiom, as opposed to any of these other 3, which would have worked equally well, he's keeping close. I think what Hilbert is doing is trying to keep as close as he can to the spirit of Euclid. Spirit of Euclid, that sounds like a very Dr. Arndt sort of thing to say. Any questions or comments about any of the congruence axioms? Let's look at some models. So, look at is R2, again, which is kind of the traditional Euclidean model we looked at with the betweenness axioms back in the last packet, where points are x comma y, lines are sets of points that satisfy a linear equation, instance is what you would expect, betweenness was intuitively obvious, but actually coming up with a specific definition was a pain in the butt. We're going back to that model for now. And no, don't make me write, I'm not going to write out those definitions again. So what I want to do instead is to see, can we come up with definitions for line segment congruence and angle congruence that'll hold true in R2. So, take a look at it. One, two. I'm going to look at two segments. Segment from 0, 0 to 2, -2. And we're also going to look at a segment from 1, 1 to 3, 3. I claim these segments are going. I claim that by our intuitive understanding of why these segments should be congruent, they're congruent. Question is, what tells us that these two line segments are congruent to each other? In other words, why is your intuition telling us that this segment up here should be congruent to this segment down here? All right, I've had enough of the Megan, Jack, and a little bit of Katie and Elaine show. Get the rest of the class involved. What makes this segment down here congruent to this segment up here? And this one is not a trick question. Look.
On this model, it's that it's the same distance. It's the same distance in the x and y direction. It's 2x and 2y for both of them.
Ooh, okay. The fact that you can move 2x and 2y over from one point to get to the other in both cases? All right. That's theoretical too, right? 2 square root of 2 squared is 2 squared is 4 plus 4 plus 4 squared root of 8. Yeah. Okay. I find this segment is also congruent to the other two. But I don't think we could say anymore that, oh, it's the same x and y distance. Move 2 over in the x and 2 over in the y anymore. But basically what I'm getting at is, Luke, I agree that tells you that you could say these two are similar, but I don't think as a definition being able to say, oh, moving the same amount of units in the x and in the y direction is necessarily going to be enough, because it won't allow for something like this segment to also be congruent to these other pairs. If you listen to my mutterings up at the board, how did I come up with this 2 square root of 2 coordinate? Yeah?
You use the Pythagorean theorem.
I use the Pythagorean theorem. So in other words, the distance from that point to this point, that point to that point, that point to that point, the straight line distance we're used to thinking about is the same in all three cases. So we can say that all 3 segments are congruent as they have the same length. I.e. the distance between each pair of points can generalize this to come up with an actual kind of straightforward equation, straightforward-ish, as compared to the betweenness definition, for how to determine if two different line segments are congruent. Or we can say, I think that if A, I'm going to refer to with coordinates A1, A2, B, I'm going to refer to by B1, B2, C, I'll refer to by C1, comma C2, D will be D1, comma D2. Then I claim we can say that segment AB is congruent to segment CD if the distance, the straight line distance from A to B is equal to the straight line distance from C to D. And using the traditional Euclidean distance, how can we write an expression that will give us the distance from A to B using the coordinates of each point? Elaine?
So distance from A to B equals the square root of A1 minus B1 squared plus A2 minus B2 squared.
Like that?
Yep.
That's exactly what I have.
10 minutes.
Yeah, it's a little bit tricky to come up with these on the fly. Yeah, basically, this is just the distance you get from the Pythagorean theorem, where if this is A1, comma A2, if this point is B1, comma B2, then you can sort of think about the distance from here to here. I'm just going to refer to as the change in x, which is what, B1, or A1 minus B1, and B1 minus A1, let's say. This will be our change in y, which will be B2 minus A2. What's that one?
I said just do an absolute value.
Okay.
You don't have to.
I don't want to.
I'm just kidding.
And then this will give us the square root of change in x squared plus change in y squared according to the Pythagorean theorem, which, yes, is going to be a result that we eventually want to have. Seeing that before someone claims, but Dr. Burstall, we don't know the Pythagorean theorem. We're working in R2. It's true there. Yes, Megan.
Shouldn't it be C1 minus D1?
Indeed it should. Change in x coordinates, square root of change in x coordinates squared plus change in y coordinates squared. And yes, Elaine, you can do this with absolute value if you want, and want to model it up by adding absolute values and having someone then ask, Dr. Russell, what happened to the absolute value sides? So we can define straight line distance or congruence of line segments by just saying the lengths of the individual line segments, which we can calculate using this sort of Pythagorean theorem square root formula. What's a little bit trickier to do is how can we define whether or not two angles are congruent? So let's see. What makes these two angles congruent to each other? The what?
Their sine or cosine is equal.
Their sine and cosine is equal. Groovy. Now how about this? Can you give me an answer that doesn't require having any numerical measurement of degrees or radians? Joel?
If you were to draw a vertical at the endpoints of line segments.
Like here and here?
Yes. Then they would be the same length.
Ooh, then this segment would have the same length as that segment? Interesting, I like this. I have one problem with it though. Technically, angles are made up of rays, so they go on forever. There's not actually an end to them. I was just being lazy by not drawing out the rest of the rays. I like your idea though, Joe. If we treated angles as having as being cut, if the rays is being cut off, then we could sort of use your idea. Yeah?
Could you either use the same idea and use the ratios and compare to each other, or you could change the lengths of both of the line segments using Congruence Axiom 1, sort of?
Take ratios of the lengths, or take ratios. Ratios of what?
So the ratio of the length to each of the lines that he had drawn between the two line segments compared to the ratio of the line segments themselves is going to be the same for the other one.
How do we know where to draw the line segments? Can I draw one here and one here? Because those aren't going to be the same.
My second idea then.
I'm nitpicking your idea, and also Joel, your idea, because I actually think that the two of you are very close. Like you just need one more. I think you just need one more thing. Look at very excited.
Use the definition for smaller than to show that however long the rays are, you could either extend them or make a segment such that the angles have lines which are congruent, and then do the straight line across.
Trying to unpack what you just said.
The definition of line segment being smaller than,
Okay.
you
Make line segments of equal. So you basically make line segments between them that have equal length to them.
on one of the lines which includes the angle. So if say it's angle ABC and then do the definition of AB smaller than DE, and so you have say DE is larger than AB, so with the definition of that, you could have the point G, which is EG is equal to AB.
I think I get what you're getting at, Luke, and I'm sorry to cut you off, but I just want to get through this because we're about at the end of class. I think you're absolutely right. Like, I'm just going to take what you're suggesting and put a slight twist on it, as well as a slight twist on Brianna and Joel, what the two of you also were suggesting. Basically what we're going to do is we're going to pick points on our two rays, or I guess on our four rays, that are all the same distance apart from the vertex, so that AB is congruent to B, is congruent to DE, is congruent to EF, is congruent to BC. Spoiler alert, by Congruence Axiom 1, there should be unique points on that rays that'll make that happen. And then take the segment from A to C and the segment from D to F. And it very much does not look like it. But if these two end up being congruent to each other, then we'll say that the two angles are congruent. I'll write that out all out more formally next time. I didn't today because we're out of time. So next time we'll write this out more formally, kind of get a nice formal definition of what it means for two angles to be congruent in R2 in a way that doesn't rely on sines and cosines and radians and degrees at all. And then from there, we will talk a little bit more about side angle side, including side angle side's relation to the first 5 congruence axioms. Hope you all have a good rest of your day. I will see you all on Wednesday.